Welcome to STEM for Girls 2022. Today we're going to be talking about the physics of ice skating, starting with Newton's third law of motion. One of the most well-known tenets of physics, for every action there is an equal and opposite reaction. That was first discovered by Isaac Newton. And it's this idea that allows skaters to move across the ice. When they push off against the ice or stroke with their skates, they are applying a force down and back against the ground. Well, the ground just pushes right back, supplying a force forward and up that propels the skaters into a glide or jump, depending on the particulars of the force that they applied. Since the forward push is resisted by only the slightest friction of the ice, the skater can glide easily. For the most part, the physics behind ice skating comes down to analyzing the movement of skates over the ice. The skaters do two things. They glide over the ice and they push off the ice with their edges, which causes a gain in speed. With practice, this combination of movements can become as effortless as walking. Another part of physics is the low friction of the skate blade with the ice. This low friction allows a skater to easily glide over the ice surface, and in addition, the physical properties of the ice allows a skater to dig in with her skate in order to go around in a turn, speed up, or stop. Smooth ice provides very little resistance against objects, like ice skates, being dragged across its surface. Compared to, say, a wooden floor, ice has much less friction. So, the question is, what is friction exactly? It's a force that resists when two objects slide against each other, dissipating their energy of motion. Friction arises because the molecules on both surfaces bond with each other and resist when the surfaces try to move away and break the bonds. The more rough and jagged something is, the more easily more of the molecules will come into contact with the molecules on the surfaces to touch it, and thus the greater force of friction they will exert. The general low level of friction on ice allows a skater to glide along the surface smoothly without friction stopping the motion as soon as it's begun. Remember Isaac Newton's first law of motion? An object in motion tends to stay in motion unless acted upon by another force. This concept is also known as inertia, and it's why ice skaters whose motion isn't being acted upon by a powerful enough force of friction tend to stay in motion unless they use another force to stop themselves. At the same time, if there were no friction at all on ice, skating would be impossible because it is the friction between the skate and the ice when a skater pushes off that starts the motion to begin with. And friction is also what allows a skater to ever come to a stop. Momentum is basically how much force it would take to stop a moving object. Essentially, the heavier something is and the faster it's going, the more momentum it will have and the harder it will be to slow it down. Angular momentum applies to a body rotating around a fixed object. The amount of angular momentum, say, a spinning skater has, depends on both the speed of the rotation and the weight and distribution of mass around the center. So, the more mass a skater extends in space, the greater angular motion the skater will have. Another fundamental law of physics holds that momentum is always conserved, meaning that unless some outside forces enter a system, its total momentum must stay constant. This law of physics explains why when a figure skater pulls in her arms when executing a turn, she spins more quickly. With arms outstretched, her mass is distributed over a greater space. When she draws her arms inwards, the distribution is reduced, so her speed must pick up to counteract this difference and keep her total momentum constant. A skater propels herself forward by pushing off the ice with a force perpendicular to the skate blade. Since the friction of the blade with the ice is almost zero, this is the only way she can propel herself forward. As a skater pushes off with her rear leg, a perpendicular force is exerted on the ice by the skate. The component of the force that points the skater forward in the direction of motion is what pushes the skater forward. At the same time, her other skate is either raised or gliding on the ice. As the skater moves forward, she then switches to the other leg and pushes off with that one, and the process is mirrored. To push off with the ice, with the greater force and accelerate faster, The skater increases the angle, which increases the component of the force in the direction of motion. A skater can also skate backwards using a gliding pattern in the shape of a lazy S, in which the skater's blades never leave the ice. However, the skater cannot push against the ice as hard as she does when skating forward, which means she's not going as fast. In this technique, the skater pushes against the ice with her push skate facing inward while her other skate glides. As the skater moves backwards, she then switches to the other leg and pushes off the ice with that one, and the process is mirrored. Thus, the physics of skating backwards is similar to the physics of skating forwards. Thanks as always for watching STEM for Girls 2022.